So this is an update of the VESC Lisp implementation. I did make a lot of progress on it, and Joel also made it every time I asked for a new feature, so in LBM, then he has implemented that. So this is a demo with one of those small 128 by 64 Oled screens. You can buy them almost anywhere. They're really, really common for things like Arduinos and Raspberry Pis, and they're also quite cheap. And I just plugged it into the COM port on the VESC to the I2C pins and a 3.3 volt, or does it say VCC? Yeah, it says VCC and ground. And then I used the general purpose I2C driver in LispBM to write to it. And here I have a demo running where it draws a rotating 3D cube. And I will show how to make the demo because it is an interesting example of that contains many of the concepts that are important to understand LBM. So we can start by going to VESC tool and then to the VESC dev tools page, and then you have the Lisp page up here. And a bit of a reminder, so LispBM or Lisp, that is a scripting language that can run on the VESC on the firmware itself. So you can upload a piece of code to it that you can edit from VESC tool, and that code will remain there, and every time you boot, it will start this script that I have uploaded to it. And you can also do all the testing and debugging and monitor variables and so on from within VESC tool. So it is really convenient to get things up and running fast if you just want to have some custom input, or if you want to add something that runs complementary to whatever other application runs on the VESC. So you can, for example, run the PPM or the ADC app, and then you can have a Lisp script running in addition that does something like update a display, or you can even do things like change settings live. So you can you can update, for example, the current limit based on the accelerometer, so that you have like an anti-wheelie function if that's something that you would need for your setup. So if you go here, then you can start by clicking on the help button if you want to figure out where to get documentation. And I've been working on this a lot on this README on GitHub, and Joel has also been working on writing general documentation about LispBM. And you can also, like before, you can join the Discord server here and go to the Lisp channel, and I can usually answer a question there, and Joel can do that too. Joel is the one who made LispBM, by the way. So if you open the documentation page, then you will come here, and as you can see, there is a lot of text here by now, but it's quite easy to navigate because you have if you use the GitHub website, for example, then you have this thing up here where you can see all the titles, and you can even start typing here and it will filter the titles. So if you wonder how to use I2C, you can just start typing and then you get all of the I2C titles, and then you can click on one. And here you can see this one, for example, and interesting with this one is that you can, if you just run it like this without any optional arguments, then it will just start the I2C driver at I think 400 kilobits per second on the COM port. But you can also choose a custom rate, and you can also choose different clock and data pins. So you can use, for example, the SWD pins to run I2C, and then you can run UART at the same time if you need to do that for some reason. So that is where to find all of the different VESC extensions. And there are a lot of extensions now, so I think up to about 200 or so. And it's not only things like I2C and motor commands, I also added some, for example, loops. What did I spell here? Loop, of course. And so before, when I was showing the demo, the first version of LBM, we didn't have any constructs for loops, so you had to do everything with recursive functions. And I mean, that works. It's really equivalent, so you can express any loop in a recursive function. But for some situations, it makes sense to just have the syntax for a loop, because it can make things easier. So now you have 4 different loops to choose from. So you have the regular for loop, and this one takes an iterator, a start expression, a condition that has to be true for it to continue, and an update function. I haven't ended up using this one so much, but it is there if you need it. And then all of the loops have the body at the end, which is the expression to execute for every iteration. The while loop is one of the more common ones I use, and a lot of the time I just do while true and have this as one of the main things, or the main loop that runs in the program. And it just takes a condition and a body. And then there is also a range loop, so you can iterate from, you can iterate this iterator from start to end, and also in the body you have access to this iterator as you have with the for loop too. And then finally there is a loop for each, so if you give it a list, then it will execute body for every element in the list, and you can access it with the iterator. And we have some examples here for all the loops. In this case, for example, we have a list of strings, and then we iterate over them, and then we print every string, and then the output would be first this one, and then this one, and this one, and so on. And also one thing to remember is that if you want to run more than one expression, then you need to enclose it in a prog n. So as you might remember in Lisp, you always have a parenthesis, and then you have a function to call, or an expression to evaluate, and everything after that are arguments to the expression. And the prog n expression simply is a function that will evaluate all of the expressions in it one after one. Okay, so that is a bit of an introduction again. And I can also mention that if you go to the beginning here, then you can see, for example, the LispBM reference manual that Joel has written. So this is mostly a quick summary of all of the different things that are in LispBM. It might not be updated fully, for example, with the association list at the moment, but that's a quick way to look up the different things. And then there is also an introduction and a Lisp processing chapter that Joel is working on. Those are not so VESC specific, those are Lisp and LispBM specific. And I think the introduction is a good start. Lisp processing, I think in many cases you don't really need to think so much about Taylor cursive functions, for example. You need to think about them more if you want to do things like implement those loop constructs if you didn't have them from start, with just things that are usually available in Lisp. But you can read about them there, and you can try them out too. So next I want to mention the REPL, and that is this line here. So in VESC tool on the Lisp page, on the lower region here, if you are in console, then at the bottom you have a REPL, and that is quite something that is really useful when you try things out. And also the introduction and in general the chapters in the manual are written kind of for interacting with the REPL to try the different things out. And here you can enter arbitrary Lisp code. So you can do, for example, +1, 2, and it will print the result up here. And the thing it prints will be whatever the code that you run here returns. But you can also run print. For example, you can do print hello. And then you can see that print hello will print hello, but the function itself will return true, and that is why you get this arrow with true as the return value of the function. So let me stop and erase the program now. I will actually do erase, and then I will just do :reset here, and that will reset LispBM. You can also note that I have pulse status active up here in this right pane here. And then you can get the CPU usage and all the variables and everything that they have in the workspace. And now you saw that I did something that was not Lisp code. So there are a few things that start with : that are kind of extra commands in the REPL to do a few different things. And if you press the question mark here, then you can get a list of them. And then you can do, for example, things like info. And what I did now is that before with reset, I just ran reset on LispBM on the VESC, and since I did erase up here before that, we don't have any script stored. That means when we reset, we will not start any code, it will just sit there and wait. So let me delete all of this code. And now I can also talk a bit about this editor, and what it does is really it runs whatever code is written here line by line. So it's the same as typing the lines into the REPL, but it will be typed into LBM every time you start it. And the REPL can also access whatever is written and in memory here. So if we do, for example, I'm here. If we, for example, do define, we define a function and we call it add2, and it takes one argument x, and the function will do the plus operation with x and 2, and then we do closing parentheses and closing. And then if you upload this one, now it will have executed that line. And you can, for example, here, we can run and if we wanted, and we can see that this function will be in the environment. Actually, it wasn't that strange. Yeah, maybe I forgot to upload it. So you have add2, and you can also see this defun macro in the environment now, because defun is not built into LBM. And then since I used it, it will look if there is something with that name that exists, and then it uses it. So that's why we also have that here. And now we can use the add2 function. So we can do add2 1, and then it returns 3. So this way we can test all the functions that we make up here. So what is the next step? Yeah, let's actually make a loop here. So we can do, and again we can go to the examples here, so we can maybe do loop. And then we can just, let's do the while loop. Just copy this thing as it is. And this will just keep running forever, and it will run a prog n, meaning that we do more than one expression. And it will print hello world and sleep for 2 seconds. And if we upload this one, then you see that it prints hello world every 2 seconds. One thing to note here is that since we ran into a loop here, it will not continue down here because we are stuck here forever now, or until we run break in the loop. So if you want to make functions before this one, then you have to, or if you want to use them in here or from the REPL, then you have to make them before you go into the loop. You can also spawn a thread that runs this loop, and then it will continue running in the REPL, and you can run as many threads as you want to. While we're at it, we can also, I think I mentioned this before, but if you go to, you see that we are in the console here now, and if you go to the third tab with examples, then you can see a lot of examples that come with VESC tool for all sorts of different things. And I want to show a bit of the plotting and variable kind of explorer thing here that can be useful. So we can see that add2 is an environment. If we type and like we did before, and a few other things, we also have this loop while macro now, but they're not listed here because this thing only lists things that are bindings. This is called a binding, by the way. Bindings that are single numbers. So if we do, for example, define, or we can even do def, that's a shorthand for define, a and 1, and then we do Control E, I did now, instead of upload, that's the same thing. You can also look for some different keyboard shortcuts here that you can use in here. So you can do things like select text and comment it and uncomment it and so on. Then you can see that we have A and it is set to 1. We can also do, for example, in the loop, we can do def A plus A1. And then you can see it will count up for every time we print hello world. And also if this one starts to be too full, you can use the erase button up here to clear it again. So let's go to the examples and look, for example, at let's look at the voltage example. And here we have a few things. So we use the raw commands from that you can find in the documentation, and they've been binding different things, and then will show up here. And then you can also on this side, we see already examples. We can go down the plot, and if you select a number of things, it will plot all of them. So if we do, for example, these, and then I have the motor over here, and if I spin the motor a bit, then you can see that we get some signal. And if we sample a bit more often, then we will get a bit higher resolution in the samples. We can go up to 99 Hertz here. So this can be useful for debugging Hall sensors and things like that, for example. So if we go to, say, the raw Hall example, then it will plot all the Hall sensors if you have them plugged in, and then you can see their states, and now all of them are showing 1 all the time because we don't have any Hall sensors plugged in to the VESC here. So let's start with the display example then. I will do that by having the example that is ready next to me here, and then I will copy in one thing at a time, and then we can try to explain it slowly. So let us do the OLED cube example, and that is the one that draws the rotating cube. The one that runs the slowest too, because it takes a lot of cycles to draw 1 pixel at a time and calculate the coordinates for each pixel and then do the 3D rotation and so on. And this is the kind of thing where a scripting language will be a weakness, because the raw throughput for very short operations is so much slower than if you have native code. So this is maybe not the most useful example of where this is powerful, but still you can run, as you saw before, you can draw this cube at 5 frames per second or so and do all the rotations and everything. So let's clear everything that we have here. And I can also show, for example, I have some, here is some C code that I found for this display. You can also look at the Arduino drivers, and they're usually really, really long. And it doesn't really take that much to get it running. So essentially what I have to do is you have to start the I2C driver, and then you have to initialize the display. And once you have initialized it, you can send just pixel data to it over I2C. So let's go ahead and do that. I will go back to the console here in case we want to print something. So I will copy these lines here first, and then I will explain what they are. Eval error. I probably forgot to, yeah, that is also something that we're going to work on, a bit better error messages. And the error in this case, you can also do, no, I don't think it will show the reason here. So let's go back here, and I think the problem here now is that I don't have the SSD address bound to anything. And now it did this, whatever I did here, and I will explain what it was shortly. So what we have to do to get this display running is we have to send a sequence of commands to it to first switch it off, and then set up the oscillators and the address and the scan direction and contrast and pre-charge and some things. And you can dive and look for all of those in the datasheet, or you can also look at some C code examples like this one here. There's this init function down here where we do more or less those things. You can also bind, you can also make, instead of typing the hex directly in here, you can also bind it to something. But I found it easy to just type it in, because when you look at the datasheet, it will just write the hex number, and that makes it easier to navigate the datasheet and doesn't make it as cluttered as it would be otherwise. I can also show some other driver that I found for this one. I don't think this is super well written, the C code, but essentially here, so the commands that run here, essentially they define that in a C array here. And this one is a bit more complicated to follow, because first they write how many commands are in this array. And the command structure in this one is usually that they have a command, and then you have 0, 1, or 2 arguments to that command. And here they write that, yeah, this is command with 0 arguments, this is with 1, so we have the command and the argument and so on. And then I have some C code here that runs all of those. And from here to the commands in the C program is essentially what we have here now. And now we write it directly to I2C, but we can also just print to the console here and see what things look like. And since, as you remember before, if I have some code here and I have uploaded it, then we can access all of that here. So we can do n, for example. Then we see that we have the commands, the init commands, which is the list. And here we use this for each loop. And in this case, we are just using the I2C, but we can also, let's see, I will comment this one and I will just print them. See. And now if we run the code, you can see that I just print those lists of 1, 2, or 3 numbers in them. So this is a way to test, to just quickly check if this works. And that's a really convenient way to loop over this list, by the way. So it will figure out when the end is by itself, and it will just have the commands there. And now if we take this thing back, then you can see that we have some odd syntax here. So we have this sign here, and then we have comma at C. So what is going on with this line? And as usually is the case, there is probably 3 or 4 different ways to do exactly the same thing. And this is a case of something called quasi-quotation. And I think quotation is one of the, if you're not used to it, it's maybe slightly tricky concepts to get around, but it is really easy once you are used to it. But essentially what it means is that when I type something in the REPL here, if I do, for example, +1, 2, it will execute the plus with the arguments 1 and 2. So if I write something in parentheses, it will always try to evaluate the first thing with the arguments, and the arguments themselves are also evaluated. So if I write 1, 1, 2, for example, then it will give me an eval error because it tries to evaluate 1, and 1 is not a function or anything, so that will not work. But I can also not evaluate it. Or suppose I just want to have a list. This is literal list. I just type in, what I'm doing here, I'm just typing the list in that will be evaluated, and by default it will assume that it should evaluate it. And there's also things like the list command, and then you evaluate the function list, which takes a variable number of arguments and creates a list of those. But you can also use quotation, so you can write a quote mark here. So instead of evaluating it, I'm just returning the list itself. And that's what I did here. So I define or I bind something to commands in it, and usually it would evaluate this expression, but I just quote it here, so I just get a list of lists. And you can, you can nest lists any way you want to. So what is the thing with quasi-quotation? So quotation, one thing is if I do this, then it will just quote the thing, and it will be kind of nested. So if I write anything here, so if I do say +1, 2, and I want to have 3 in this position, that will not happen. You see that it will just put that list in here too, so it will not evaluate anything within the quote. But I can also use quasi-quotation. So in that case, I can replace this quote with this other quote, and if I run the same thing again, exactly the same thing happens. But then I can use a comma in here for example. And now you see that I got 3 here, and the quasi-quotation means that quote this, but anything that I put comma in front of, evaluate that expression and put that into my quotation. So this way you can build up different lists. And that is what I did here, but I also have this @ character. So what is this one about? I can explain that here too. So if we do def A5, and then we do just the whole quotation thing again. So if we just do A with the quasi-quotation here, we see that I just get 8 because I didn't evaluate A. If I do comma A, it will evaluate A and put that in the list. But A is just a number now. So what if A is a list? And here quotation comes in again. So if I do, suppose I want to have 5, 6. If I do this, it will not work because it tries to evaluate 5. So I can also quote that here. And now if I do A, you see that A is 5, 6. Now what happens if I do this again? So now we have 1, 1, 2. But you only have one element here, and that element is a list itself. So this is kind of a tree. And that's not what we want here. We want these two to be part of that list. And that is what the at character does. So if I do comma at, then it will splice that list into this list. So that is where that comes from. So now we have explained the syntax here. So we do quasi-quotation, and we do 0, and then we splice in the what is called the element of this that we iterate over every time. And the reason we do that is that if you look at the protocol for the display to send commands, then you have to send it a 0 first, and 0 means that I'm sending in a command now, the display. And after the command, you should have the command and 0, 1, or 2 arguments to that command. So this is simply a way to build that list, and we can also test it. So instead of doing this, we can do print here. And run that again. And now you can see that we have exactly the same list, but we put the 0 in front of every element here. So that is one way to do that. And something that I will not go into now, but you can think about it. So we can remove the quotation mark, and we could, for example, do list, and then you will see, and do it like this. What do I do now? Then you see that we have this situation again, that we have one list that contains another list inside. But as it turns out, we can also do cons here that I will not talk about now. But this is what chapter 2 talks about, why this works. And the very, very short answer is that every list in Lisp is actually a linked list of pairs. So the list is not the most basic element, the pair is the most basic element. And a list is just a pair that contains the first element, and the second element is another pair that contains the next element, which contains, and then another pair which contains the next one, and so on, with a nil at the end. And that makes it easy to append something to the beginning of a list, but a bit harder to append it to the end. So that is where this comes from. And let's go back here. So now we talked about the for each loop, we talked about quotation and the list, we talked about quasi-quotation and splicing in parts of the list. And I can also mention at this point that usually when you do programs in Lisp for most things that you probably will do on the VESC, you don't have to think about even these concepts, but that's why I mention it here, because or why I use the display example here, because this is a nice example of that demonstrates some of those concepts that I happen to stumble upon quite a bit in Lisp. We can also go back to this thing here, so to the quotation here, so you see that we do I2C start, and then we have use the first optional argument, and you can see that this one is quoted as well. And quoting it means that we would just pass in the symbol. If I wouldn't have this quoted, then it would try to evaluate that symbol and pass it in, and if you do that, it will not like that, because this symbol is not bound to anything, it's just a symbol. And this function works by just looking at the symbol, and if it is this symbol, it knows that it should start the I2C at 700k kilobits. So at this point, we have the display initialized. Now I will mention another thing that is a bit of an extra thing here that is probably not present in most other Lisps, and that is native arrays. And those are, in this case, are low-level arrays, so they are literally a byte array on C memory that you can pass to C functions. And that is useful when you have something like this display where you have 128 by 64 pixels. So it means that you have, you can use this as a calculator too, times 128, 64. So we have 8,000 different pixels, and that takes some memory, and if you store them in a linked list where every element in the list takes 2 times 32 bytes, then it will run out of memory fast. So this way you can just use an array directly. By the way, it will not use this many bytes because every pixel in the display is just on or off, so everything is actually a bit. So it's not more than 1K that we need as a buffer for it. So let's move on with that. So go to this example, and now we have initialized the display, and then I will copy these 3 lines. And run the code again. And I ran it again because now I have it in memory. And then we can do, for example, pics, or we can just type like this. And what happened there? It looks like a string. And the thing is that arrays and strings are the same thing in LispBM. So let's go back to what we did here. So we have pixbuff, and then we use array create, and this is a byte array. Actually, we can remove this type because it will assume that it is a byte array by default, so we can just keep it like this. And the length of it is 1025 bytes. And why 25? The reason is that, as I mentioned before, we have 1024 different bytes that we need to, well, describe all the pixels, and every bit and every byte is 1 pixel. But one thing to make it a bit more convenient to update the display is to embed the command to write to the display in the same array. And that is why we add another byte in the beginning, which we set to 0x40. And this tells the display that if we send this, then we are sending pixel data. And then it will not, so instead of interpreting it as a command, which we do with 0x00 or 0, we send 0x40, which will interpret this as pixel data, and then the rest of the vector will just be all the bytes. So we can try just writing that. I think I have this command here. So all we need to do to write this pixel buffer to this display is do this. Yeah, I can also mention this one, that buff clear sets everything to 0 in this case, and what the arguments are. The first argument is what to clear the buffer to, and the second argument is where to start. And this is also one of those things. So if you go to the documentation and you search for buff clear, then it will describe what this one does, and it will also show some examples here. And it will show that you have 3 optional arguments. So this is the buffer itself you want to clear, the byte to clear to, and where to start, and optional length, so you can clear some region in it if you want to only. So what have we done here now? We have initialized the display, and we created an array of 1025 elements, where the first one is the command to write the pixels, and the rest are the pixels themselves. And we cleared the buffer from pixel 1 and onwards. So if we do this now and run this code, then we should see a clear screen. Let's see if that worked. So we have the camera here. Make this one always on top, and then we run the code. And now you see we have a blank screen here. It could also be blank because we did something wrong, but I'm pretty sure that it worked because, well, I've been running this code before. So now we have a pixel buffer where we can write our pixels, and we can send that to the display, and we have it initialized. So we could, for example, do there's a bunch of buffer commands, by the way, to work with the byte arrays. So you can, for example, do buff set. There's also buff set bit, so you can set a bit that's an offset. So you can say, let's use this one and just switch on some pixel in it. So buff set bit, and then we do pix buff, and we set bit 135 to 1. Control E, And now if I zoom in here, let's see where my controls have gone. This one. So I can see that we have one pixel here that is lit up on display, so we can write the different pixels to it. Let's figure out how to draw lines. Now, I will not go too deeply into this, but the first thing we need to have is a function to set the pixel at an x and y coordinate. And if you stare at it for long enough, then you can figure out what this one does. But briefly, the way the display is arranged, I think I have another thing up here that I can use as an example. I will go into the line drawing in a bit. So you have all of those pixels, and then every byte is arranged like this, so you set them from the top to the bottom. And then, so this would be one byte, this would be the next byte, and so on. So if you want to set pixel, say x this much, how much is this, like 6, and y 4, like this pixel, why did I click on it? Then you have to set byte number 1, 2, 3, 4, no, 0, 1, 2, 3, 4, 5, and bit 0, 1, 2, 3 in that byte. And this is essentially the calculation that this one does. And it takes the bit coordinate for that byte, if that makes sense. But now we have a pixset function, and we can try to set a few pixels, or we can just go straight to the line drawing. And that's actually what I had up here in the browser. So as it turns out, it is slightly tricky to draw a line on a display and calculate all the pixel coordinates. So you can see this illustration here, that if you want to draw the line here, then one way to approximate that line would be to light up the pixels that are gray here. And one way to do that is this Bresham's line algorithm. And then if you read this article, you can see some equations for it, and then it talks about that depending on the slope, or if you start from here and go this direction, or from here and go in this direction, then you have some different versions or cases that you have to cover. And then in the end they show an algorithm where they combine all of that, and then you have this thing here where you have a start position and an end position, and it will draw a line between these two pixels. So this is the thing we want to implement. And if we would have done this before, this would have been slightly tricky, because you can see that we have a loop here, then you have to make a recursive function, but we also have breaks. So how do you do a break in a recursive Lisp function? Yeah, of course you can do that as well if you sit and stare at it, but it would be nice if you have all of the constructs in the language itself, so it's quite easy to just copy this Wikipedia code and do the same thing. And with the things we have now, that is exactly what I did. Let's see if I can make this one not go away. It doesn't let me make it always on top. That's strange. Yeah, it doesn't matter. So that is the line function in LispBM. And we'll put it here after the pixset. And then if we stare at this one together with the code here, we can see that we have more or less exactly the same thing. And now I can also introduce this thing called let. And let means that you start a local environment where you can make some bindings. And in this case we make those things here and set them to the things here, and then we can use them within this environment. And once you leave this environment, then they will not be present in the global environment anymore. So you can see that we just call them exactly the same things and use the same functions here. And as you can see, it looks very similar. It's only that here you see that we have an apps function that takes 2 arguments. And in this case, we have the apps function on the outside. Yeah, it's still on the outside. And then instead of having this one and the operator here, and the next one, we have the operator in the beginning. So we take the minus function of this one and this one, take the absolute value of that and bend it to dx and so on. And then the rest is the same. And here we use this pixset. Their plot thing means pixset in R. I could have called this one plot too, but I think pixset makes a bit more sense in this case. So And then we can also see that we have setvar, that is, I don't think we had this before either. And this lets you update things in the global or local environment. And the local environment will shadow the global one if you have the same things in both. And this wouldn't look so nice if you are a functional programmer, because you go and you create some state here and then you modify your state as you go. And otherwise, if you have state that is modified and you express that traditionally in something like Lisp, then you would have a recursive function that takes the state as arguments into itself and carries that with it. But yeah, as I said, we could have made that here too. But if we have this syntax available, then we can just copy and paste this more or less, and it's quite easy to get something like this going. So let's try this one out. Let's put the display back here, and we can zoom in a bit again. And we can upload this code. And now we can use the REPL actually. Let's see, we use the line function, line, and let's say we can say that, by the way, mention that up in the left corner, this is the 0 position, and X increases in this direction and Y increases in this direction. So if we want to draw a line from, say, X10 to and Y4 to X, and X goes all the way to 128, so let's do 100, and Y goes to 64, so let's do 32. Then we should draw a line from here to here, something maybe. And let's run the code. And you see that we didn't draw any line. And that is because we have only updated the pixel buffer, I haven't updated the display yet. So we can just copy and paste this line and run it. And you can see that we have a line here now. So this draw line, this line thing, it just updated our buffer. And then we write the buffer to the display. And this is one way to, well, draw some graphics. And that is what all the other examples do. So let's move on to the rotating cube. That will also show some, I think we talked about all of this briefly at least, but it will just reiterate some of a few things here. So one way to define a cube, this code I probably also, or certainly also found somewhere on the internet, to draw a rotating 3D cube, because that's a nice demo. So one way to do that, first is to start by defining the cube. And we can define it in terms of nodes and edges. And in this case, the nodes are the corners of the cube. And we have, how many corners do we have? I think we have 6. Or is it 8? Oh, it's 6 corners. 1, 2, 3, 4, 5, 6. 7, 8. No, it's actually 8 corners. Yeah, of course, a cube has 8 corners. Getting tired. And then the edges essentially describe which nodes we should draw edges between. So this one, and here we have 12 edges. And here, for example, the first edge goes from node 0, this one, to node 1, this one. And the next one goes from node 1, this one, to node 3, this one, and so on. So this describes all the edges. So let's go back to the code we have here, and then we have this draw edges function. And let's copy and paste that in here. And then we can, actually let's upload that and try draw edges, see if that works. And this, and yeah, now we have a cube. It doesn't look very 3D, and the reason is that we haven't rotated it yet. And we can also, while we're at it, copy in this rotate function. And then I will explain shortly how they work. So we do rotate, and now first we have to upload it again. And then we can do draw edges, and we can update it, and then we can rotate, and we can rotate the edges, say, by 0.8 and 0.2 radians. And then we can do draw edges again and write it. And now you can see that we have two cubes on top of each other, and the reason is that we didn't clear the buffer before we did the next one. And while we're at it, we can just take the whole animation code, which is not a lot here. We'll skip the font here. And then we can see what this one does. So we don't do any put string, and we can remove the frame rate calculations on. So if we run this code, then we should have a rotating cube here, hopefully. Yeah, you see that it rotates now. So what is going on here? So we have the nodes and the edges, and this function draws the edges. So one thing to note here is that all of these are just 1 pixel wide, and we have everything centered around an origin. So it would be a cube that is up in this corner, going around this corner 1 pixel in size. So in addition to drawing this, we also want to translate it, this much in X and this much in Y, and we also want to scale it up a bit. So let's, in the draw edges thing, we make a local environment again, and then we make a scale variable, and then offset X and then offset Y, and I define them like the pixel offsets divided by scale, and you will see, hopefully see shortly why we did that. So now we have those set, and now we want to draw the edges. So we loop over all the edges. So we use the for each loop again, and for every edge we're gonna get E as a variable in here. And for every edge we want to get the 2 nodes that this edge points to. So in this case again we make a let environment, and we call the node A and node B, and the nodes are IX. You can also see this in the documentation. So IX means, we can actually show that a bit. So if you do IX of nodes 5, then you can see that we have 0, 1, 2, 3, 4, 5. So we got this one now, but it is not the numbers that we see here. That's because we have been running the rotation on it a few times. So here we have the first node of the edge that we look at, and this is the second node of the edge that we look at. And now we want to draw a line, and one way to, so what we want to do here really is we have those nodes in 3-dimensional coordinates, and to project those 3-dimensional coordinates onto the plane of the display, we can, and if we just do a projection without perspective, it's quite easy. Then we just take the X and Y coordinates of those nodes and draw lines between them. So that is fairly easy. So we have the nodes here, and we want to draw a line from the X, which is the first one. We do index again, so we can also just illustrate that here. So we now do the index node 5, and we can also index that, because that these are lists within a list, and we do index 1, then we just get a single number here, which would be this number, but it's not the same now because we have rotated a bit since it was running here. You can also see, by the way, that this loop just runs, everything gets updated. We can still run REPL commands, and we can see everything that this one does. And by the way, we also do something now here that functional programmers usually don't like, and that is that we, with the rotate function that I haven't gone into, update all of these coordinates. So we do a destructive update here, and usually that's not something that people like in functional programming, but yeah, that's one way to do it here, and it doesn't really matter that much when we have so little code. So anyway, so we have the 2 nodes, and we want to draw a line between them, and we want to scale them, and we want to offset them. So in this case we make a list, and in the list we have 4 elements, and the first element is the X offset plus the X coordinate of node A. The next element is the Y offset plus the, what is that? The Y coordinate of node A. And the same thing for node B. So now we have added the offset to them, but we also want to scale it. So the offset we do by just adding it to the X and Y correspondingly, but the scaling we just have to multiply everything by something. And the way that we do it here And again, this is something that you can do in 10 different ways, but this is one convenient syntax that you can use in functional programming. So for that, we use the map function. And finally, when we do this, we're going to get a floating point number, and we want to have an integer, so we can also use 2i on that. So for that, we use the map function. And the map function is simply, that is a higher order function that takes the first argument is a function, and the second argument is a list. And the map function will apply that function to every element in the list and create a new list with those applications, and it will return that list. And then we want to run the line function with this list, and the line function doesn't take one list as an argument, it takes a bunch of arguments. And the apply function means that take this list and pass it as arguments to the line function. We can also try map down here, and I can also mention that this anonymous function syntax, what that looks like. So if we do, for example, map, and then we create a function here, you can do lambda, or you can type fn as function. They mean the same thing. So we take a function that takes one argument x, and that function will take, for example, do x plus 1. So this is our function, and then we want to get the list, and then we use quotation again, because otherwise it will evaluate that thing, and then we do 1, 2, 3. Close all the parentheses. And now you see that we have a list of 2, 3, 4. So what we did is we used map on this function that takes one argument x, which will be every argument in this list, and applied it to this list, and it will increase all of them with 1. And then we can also show apply, for example. Now this is a list, and you know that the plus operator, 1, 2, 3, it can take an arbitrary number of arguments, but we cannot give it a list. Let's do quotation again. So it will not like that. That is a type error. And then we can actually, if we want that to work, we can just do apply here. And then it will work. And apply will pass in this list as arguments to this one. So if you put all of this together, if we do this other thing again, so we do the map thing, and maybe we want to have the sum of a resulting list, then make another parenthesis around it. And first we try just plus, which will not work because it's a list and not a bunch of arguments. And then we use apply. And that's essentially what we did up here. And you don't have to make it that way, but you see that it is quite compact, the syntax. And in this function that we took one element x, which is those 4 indexes with the offset, and then we multiplied them by the scale that we set up here. And then we use this 2i, and this is a type conversion. So for example, if you do, say, 3.2, that is floating point number. And if you do 2i on it, then it will do the floor on that and convert it to an integer. And that is necessary because we use things up here like the modulo operator, and it doesn't make as much sense on a floating point number, and you don't have, yeah, it actually does, and I think it even works on floats, but it will not work as an index in this pixel buffer because I only have whole indexes. So that is why we can do all of that in this one operation. So that is how we draw all of the nodes here, and or all of the edges. Should I repeat it again? No, let's not repeat it. And then we have this rotate function, and I will not go over this one too much in detail, but essentially it is a rotation matrix. So you have an angle in the x direction and y, whatever those directions means. I think I just copied this from somewhere. But then it does the let thing again, makes an environment, and binds the sx and cx, which means sine x and cosine x, to the application of the sine and cosine function of those. And then we go over all of the nodes. We use loop for each again, and we use let here again, and then we have a prog in here where we just use set ix, and set ix is a destructive update of a list. And I can also show that. So if we do def a quotation again, 1, 2, 3, and we do A, then the list A is 1, 2, 3, and then we can also do set IX A, and what was the syntax again? Yeah, first the list and then the index, so say index 1, and set that to 15. And then A will be this number. So now we did an destructive update of A. And here again we can see that we loop over the nodes. So this is a list of lists, and then for each node we will have an n, and then we do set IX on the different elements of n to updo the rotation. So then we have our main program. So, and at this point we have already executed all of the code on the way down here, and to remind you, this is not going to execute this thing. This just makes a function and binds that function to the symbol line. So now we just have that function available once we passed here. And once we passed here, we have those available. We could actually move them down, because even if we use them in here, we don't need them here because we haven't executed those functions yet. So just to illustrate that. Should still be working. Yep. And then we do our main loop. So we do draw edges, then we rotate them a bit, and then we write this to the display. Then we do buff clear, because if you wouldn't do buff clear, that might look interesting. Let's try that. Then you see that it will just draw over itself all the time. Also quite interesting to look at. But buff clear will just like this, will just clear the buffer except element 0, which is the address. And then we write it after we do the clear after writing it, and then we sleep for 10 milliseconds. But it will obviously not run at this speed because this is quite computation heavy. You can see that we're using a lot of CPU here. And calculating individual pixel coordinates is not something that a high level interpreted language is the strongest at, but you can still see you get this frame rates, and we're doing quite a lot of calculations in sine and cosine and rotations and so on, so you can get some decent performance out of it. And we can also quickly look at how to implement a font here. No, let's skip the font. We can just assume that we have it. I can mention it quickly. So the font, the way we have done it here is that we just have a font table. And this, by the way, is also a byte array. And the square bracket notation means that we create a byte array in Lisp and bind it to font. And then it will behave the same as the byte arrays or strings. And the font essentially means, in this case, this is a small font, so this is constructed with the assumption that when we write it to the display, we have the pixels start from up here, and then count to 1, 2, 3, 4, 5, 6, 7, 8, next byte 1, 2, 3, 4, 5, 6, 7, 8, and so on. And making it that way makes it quite easy, because if you want to write one character, then we can just copy from the font, from the character position to the pixel buffer, and we can copy the number of 5 bytes in this case. We can also have a quick look at the buff copy function in the manual. So buff copy, and then you see that you have array 1, index 1, array 2, index 2, and length. So you copy, this is the target, this is the index of the target, this is the one to copy from, this is the index, and this is the length. So this is essentially exactly the same thing as the memcopy function in C, if you're familiar with that. But this one does boundary checking, so if you try to copy outside of any of the arrays, it will only copy the things that are inside. And that is also one of the things that I took care to do in this LispBM implementation, or the extensions, that it does a lot of checking along the way, so you cannot easily use something like buff copy to write to the memory elsewhere and make the motor short out to something. Hopefully, at least. But so far it seems really robust this way, with all of the error checking is on. Also, as noticed before, this runs on a different thread, and if I do something here that is an error, if I type some nonsense here, the rest will still keep running. So if you have multiple threads running and one of them crashes or does something, the rest will still keep running, and you could even have some monitoring thing that responds them. So it is quite easy to, it is quite forgiving, and it's fairly easy to write code that is where you don't have to take as much care to not mess things up. So I think this is a quick and fairly safe way to do quick programs and applications. And it also, as I mentioned before, it takes care of garbage collection, everything for you. So yeah, font, that is how the font works, and then we can make this putc thing that just does a buff copy to copy it into the big buffer. And then we can also use a put string function that takes in an X position in this case, where the stack should start, which row it should start on. It makes it a lot easier if we split the display into rows. Then we can get, how many rows do we get? The font is 8 pixels high and we have 64 height, so we get 8 different rows. And then we'll use this range loop again and loop over the string and use this putc function for every character. And we can copy that in here as well. Just put it here. And then we can do example here. Put str, and then we do x. Say, suppose we want to have a string that starts up in the left corner here. So we start at x0, row 0, and we put in where did it go? Hello. Execute the code again. And now I see that we have hello up here in the display. Took a bit of a pause there, had a phone call. Yeah, so now we have printed hello to the display, and that is quite easy, as you can see. So created a font here, or this font I actually just took from one of the other C projects, or I can also use for, I have this font generator for the one that I could also use to generate a font like this. That is made according to how the display looks or is organized, and then we can print to it using that font. And we can also use a bunch of the string functions in LispBM that I will mention briefly. So let's see. Let's actually print some voltages on the display. Let's get rid of the cube for now. And we could use a bit of a bigger font. This one is only 5 characters wide and 8 characters high. I think I have one 8 by 16 as well in another example. If we go to examples and we do the large font example, then we can copy this font. And this one is a bit more complicated because I have to do 2 buff copies, since we have to do the upper and lower part, but still not so bad. So let's see if this works, or if we will run out of memory now that we have the cube drawing and everything in this large font array together with the large frame buffer. Paste it in. Upload. Yeah, now we have a bigger text. So that will be easier to see. And now I will, I still need to write it, but I will comment these out. So we'll only do the hello, and now it will update a bit faster. Let's print the motor RPM here. So in order to do string manipulation, that is actually a really strong part in LispBM. So you have a lot of string functions. Let's go to string manipulation. And we can start by, there is this string from n, for example, where you can create a string from a number. And you can also use the format argument. And in the format argument, you can actually sneak in some other characters too. So let's copy this one. And then just replace hello with, let's see, got some new line character in there. String from n. And we can do, for example, v in the input voltage, and we will control E. And that's 2.5, just because I said it is now. But we can actually get the voltage too. So we can do get V in 20.8. And now if I go to the power supply, let's see. If I change the voltage, you can see that it updates, and it does it quite quickly now, because yeah, you can also see we're using a lot of CPU because I don't really wait a lot with trying to do it at 100 Hz. But these updates will be quite fast because we can take advantage of the fact that the buff copy operation so fast. So we just do a bunch of buff copies and then we tell the I2C to send it to the display. So we're probably even at this, probably at 30 Hz or something. I'm gonna measure that now. So we can also do, say, this is one line. So let's see, say we have one line with the input voltage, do another line with the, say, RPM. Can align them, and then we can do, how do we get the RPM? RPM, get RPM. Yeah, just get RPM. And maybe 0 decimals precision is enough. And this will probably not work. Or it will work, but I think we'll just write it over the input voltage. So let's write this on row 1. I think row 1 will not work because we have double rows now. So we'll kind of write over half of it. So row 2 with the big font. So now we have the input voltage and the RPM. And let's see, where did the camera controls go? Have them here. Can zoom out a bit. Maybe that's a bit much. But if I spin the motor here by hand, zoom in a bit more so you can see that. Or maybe make this one bigger. I can see that we can plot the RPM. So that was fairly easy too. Yeah, long video and hopefully not too unorganized, but hopefully it's useful to get a bit more going with the Lisp scripting.